Let me start introducing our speaker. Our speaker tonight is Dr. Saana Isojunno, who is a behavioral ecologist at the University of St. Andrews in Scotland. Saana is based at the Center for Research into Ecological and Environmental Modeling, and she works closely with the Sea Mammal Research Unit. She majored in fisheries and hydrobiology at the University of Jyväskylä in Finland before moving to St. Andrews, where she earned both a master's degree and a PhD, working on sperm whale foraging behavior and anthropogenic disturbance. Her research focuses on how animals cope with environmental stressors and human activities. So today's presentation will focus on auditory masking, an issue faced by many marine mammals that exist entirely in the water and who use vocalizations to communicate with one another or use echolocation to forage. Specifically, we'll hear from Saana about work that investigated whether sperm whales exhibited behaviors consistent with masking, and the project used experimental exposures to Navy sonar and wind-generated surface noise. The paper upon which the presentation is based is currently in early view, not yet assigned to an issue of the journal. It's entitled "Sperm Whales Exhibit Variation in Echolocation Tactics with Depth and Sea State, but Not Naval Sonar Exposures." There's a long list of co-authors, so I won't read them off. I assume Saana will probably have a slide that shows you who her co-authors are. With that, I'm going to turn it over to Saana to begin her presentation. Thank you.
Thank you. Thank you very much for the kind introduction, and thank you for having me. It's a real pleasure and for organizing the series. All right, let's see if I can share the presentation. And I'll also share the sound. Yes. Okay, so Daryl already covered the title slide. So I'll just go straight into talking about what I'm going to talk about. So in the next 40 minutes or so, I'll give you first a bit of a background on the study system, which is sperm whales and Navy sonar in North Norway. And then a brief recap on auditory masking and the basic concepts before going on to how we study masking or have studied masking in sperm whales. And we took both a theoretical modeling approach, which then guided a more data-driven approach. And I'll close with some future corrections and conclusions. So the study system. So sperm whales have a cosmopolitan distribution around the globe. Our study area was in North Norway. So while both males and females can be found on the lower latitude breeding and feeding grounds, it's only males typically that migrate to these higher latitude, highly productive feeding areas. So for my PhD research, I studied both the male sperm whales in North Norway as well as in New Zealand in the Kaikoura Canyon area. And this picture here is a sperm whale resting underwater with a typical head-up posture. So the Sea Mammals and Sonar Safety Project has conducted sonar trials in North Norway to better understand the safe levels of sonar in different species. So not just sperm whales, but also humpback whales, northern bottlenose whales, pilot whales, minke whales, and killer whales. So it's a multinational collaboration, and you can see our the research vessel that we use by the Norwegian Defence Establishment. So the sonar trials involve taking Sperm, the research vessel, out with a tack boat attached to its side, and we'll track visually and acoustically whales at sea. And once we are ready and have located the whales, we'll launch the tack boat. We carefully approach the whale from behind with this long carbon fiber poles with the suction cup attached D-tag, which is a sound and movement recording tag. And once the tag is on with the suction cups. We then track the whale for about 4 hours and kind of leaving the whale be and do its own thing. So you can see the vessel track in those rectangle tracks around the whale with the blue dots showing the visual fixes. So the first experimental treatment that we always do is a no sonar control approach. So this involves leaving the whale, moving further away up to 10 kilometers, and then approaching the last fix of the whale for 40 minutes. And for the no sonar control approach, we tow the sonars first, but it's not transmitting. This is then followed with a post-exposure period to, again, relocate the whale and make sure everything is going well. We do careful mitigation of the behaviors. Then we repeat the kind of approach, but now with the sonar source. So the data that comes back from the detect, so we go and actually physically recover the tag afterwards. It has a VHF, so we can go and locate it at sea. So from the sound and movement recording tags, we get the dive profile, which is plotted here. So in blue are the regular clicking, which indicates long-range echolocation, and then buzzes indicating prey capture attempts, so short-range echolocation. And here you can see the kind of quite a strong cessation of foraging response for the sonar, which is highlighted in yellow. So you can see that the regular clicking becomes more intermittent and there's no buzzing during the dive. There's also some codas produced, which are social click, and also some slow clicks for which the function is still uncertain, but we don't see them in the pre-exposure in this case. It's probably a response to the sonar as well. And then the whale resumes foraging soon after. So you can see the regular clicking and buzzing again appearing on the dive profile. So from the movement sensors, we get, as well as depth, we get pitch, roll, and heading. So here in the middle panel, I've shown the absolute value of pitch. And this is useful not only to kind of determine the whale's descend and ascending, but also those resting periods when the whale has this kind of steeper posture, either head up or head down. And I use these sound and movement data in a hidden Markov model that estimates 6 different behavior states. And that's what the bottom panel shows, is the probability of being in one of these states. That is the outcome of the model. So the surfacing, descending to and ascending from prey layers, and then resting, and then other non-foraging, non-resting behavior. So in this case, it's picking up that non-foraging active period, which kind of indicates it's not resting, it's still active. With the baseline data, we have found that the sperm whales in Norway engage in a depth-dependent foraging strategy. So in this 2018 paper, we looked at how buzzes might cluster by the movement metrics, and we found 4 kind of stable clusters across the years. So the movement metrics included well, that's not actually a movement metric, but rather the inter-buzz interval is the time between buzzes. And then the movement metrics were vertical velocity, overall dynamic body acceleration, pitch variance, and heading variance. And although we didn't include depth in this buzz classification, the outcome clusters were strongly depth dependent. And that's what is shown on the y-axis in those small plots. And I've also plotted the shallow buzzes, which are in cyan and in red, which are called mid-active and shallow spars, in the dive profile. Just a couple of examples of how in the same dive profile you might have these kind of shallow buzzes as well as the deep buzzes. And they're quite distinct. So the shallow buzzes tend to be longer and more active. So you can see higher ODBA values, higher pitch variance, higher heading variance for these. Whereas the deep buzzes tended to be shorter and less active. So we didn't include sound metrics in the classification, but when you look at the acoustic characteristics of these buzzes, they also differ between the 4 clusters. So here's clicking rate on the y-axis on the left-hand side, and the right-hand side is the apparent output level. So we call it apparent because the hydrophones are on the back of the whale rather than in front of their nose, which is actually the sound beam. And so what we get on the back of the whale is a kind of only a proxy of what the actual sound output will be. So from here, these plots, I just wanted to point out that the click rates of these beeper buzzes tend to be slower, whereas the click rates of the shallow buzzes tend to be faster. And because of this movement activity, we think that this is because the whales are potentially approaching faster, more maneuverable prey that are harder to capture. And with these buzz rates being deeper in these deep dives as well, it kind of indicates that they're going for something that's easier to capture and more abundant during these deep dives. And when I say deep dives, I guess I mean anything below 500 meters, but especially in the 1,000 kilometer, 1,000 meter, 2,000 meter depth. So navies have advanced their sonar technologies over the years. Traditionally, the sonar has involved emitting a ping and then listening for echoes. So this is the kind of traditional pulsed active sonar, which I abbreviate as PAS here. So the duty cycles are about 5 to 10%, meaning 5% of the time this sonar is
We seem to be having technical difficulties. I'm not sure. Okay, there we go.
okay. Do you know where you heard until?
Sorry, Saana, are you still presenting or have you gotten cut off?
I got cut off, but I can reshare my screen. If you just tell me where you heard me to, then I can start from there.
Okay.
If you can all hear me now, I guess I can start over from this slide.
Okay, go ahead.
Okay, so new sonar technology. So the traditional sonar that navies have used is pulsed active sonar. So where you have a signal and then you listen for a while, whereas the new technology allows for more continuous transmission and listening for sonar signals. So this involves much higher duty cycles, 90 to 95% compared to kind of the traditional 5 to 10%. So the amplitude of these new continuous active sonar signals don't need to be quite as high, but because the duty cycles are longer and the signals might be longer, then the overall energy that you're putting into the ocean might be higher. And because there's all these narrow gaps between the emitted signals, then of course the noise is more continuous, and this raises questions for the environmental impact and especially for masking. So looking at the data. Okay, so in the 2016 and 2017 3S project then set up new trials to look at the effect of continuous sonar versus this pulsed sonar. And for this, we conducted 4 types of treatments. So the usual no sonar controls, then the continuous sonar and pulse sonar at 2 levels, at high level and medium level. And our expectation was that if sound pressure levels, so the kind of amplitude of the signal was driving the response, we expected the animals to respond most to the high level pulse sonar. Whereas if the energy level was important, then we expected similar level of responsiveness to the continuous and the high level pulsed active sonars because they were matched in their energy level. Whereas if duty cycle was driving the response, we were expecting to see the greatest responsiveness to the new CAS exposures. And what we found was that when you look at cessation of foraging, so the non-foraging active time that I talked about earlier, there was a marked increase during the CAS and the HPAS trials. So really supporting the idea that maybe sound energy level is driving these responses. So there was no statistical difference between the responses to these 2 exposures. But looking at the data then, there was actually quite a lot of whales and instances where the whales apparently continued foraging throughout these exposures. So in this dive profile, you can see again the regular clicking, long-range echolocation, and the buzz clicking kind of continuing throughout the CAS, the HPAS, and the MPAS exposures. And it was sometimes actually a little difficult to see if there were any behavioral changes, or maybe the behavioral changes were more subtle. So this then raised the question of whether these whales might be affected in a more subtle way. For example, are they still managing to hear the return echoes from the regular clicks or the buzz clicks? Are they being still successful in capturing prey? Are they having to work harder? So here's an example buzz during CAS, which seemed particularly long. So I'll just play it here. So you should hear the rapid clicking, which is the buzz, and the upsweep of the sonar with a brief break before the next upsweep starts.
We're not hearing anything, Saana.
Sorry?
We're not hearing anything.
Oh, I'm so sorry.
Someone has asked if you shared sound.
Yes, I did it earlier, but now it has unticked. So my apologies. Shall we try again? So that was the end of the buzz. So I can show you a little bit from the start again. So yeah, our question here was, is this continuous sonar in the background affecting this buzzing behavior in perhaps more subtle ways? So let's think about masking a little bit more then. What is auditory masking? So I think we all have probably first-hand experience of what it is when you're in a loud rock concert and somebody's trying to tell you something and you can't quite make it out what it is, and you have to really raise your voice in order to be heard. And it's really a perceptual phenomenon in the sense that it happens in the inner ear, in the basilar membrane, and in the auditory nervous system. And we often talk about energetic versus information masking, where energetic masking is really about being able to detect the sound in the first place, whereas informational masking can be more about the interference of one sound by another sound. So perhaps you won't be able to recognize the sound so well. So in this example, you can hear that your friend is saying something, but you can't quite understand what they are saying. So in the simplest case, you can think about a masker and a signal that are both pure tones. And the kind of region of interference of the mask can be kind of illustrated as a skirt around the masker in frequency. So where underneath everything underneath the skirt is inaudible, and the skirt is defined by the mask threshold. So to remove this masking, we talk about masking release. And one that I also already mentioned was increasing the signal, so speaking louder. So you can bring up the signal above the mask threshold. And this is called Lombard effect when it is essentially kind of automatic, and people do that without even thinking about it in increased background noise. The other way to release masking that is kind of clear from this figure is shifting the signal frequency away from the masker. So here, instead of increasing the signal level, just shifting the frequency apart from the masker frequency. And here I also wanted to point out the masker skirt is not actually symmetric. So there is a little bit of a right tail to this masking skirt, showing that maskers tend to mask signals above it rather than below it more readily. In the marine mammal literature, I guess a lot of it covers broadband noise masking. So when the masker is not a pure tone, but rather it has energy across a broad frequency spectrum. And one term that crops up is the critical ratio, which in very simple terms can be described as the signal to noise ratio that is required for a signal to be audible above this background noise. So here's a nice paper kind of reviewing communication masking in marine mammals by Erbe and colleagues. And there's really different factors they need to consider in natural environments: the sender and the receiver, and then the habitat in which they're placed in. So I already talked about source level and the spectral characteristics of the signal that is emitted, but also the location of the sender, emission directionality, redundancy of information are important to think about. So especially in terms of location and directionality, this can influence how much the masking can be released in space, as well as in time and spectral domains. At the receiver end, again, the location of the receiver, hearing is directional, critical ratios, the frequency resolution of the ear, and auditory integration times. And as well as the masker of interest, there might be other types of ambient noise in the environment, and of course the propagation environment, so reflection, refraction, scattering of sound as it travels through water, spreading loss and absorption. So now transferring this knowledge to this in communication masking to echolocation, what might masking of echolocation look like? So here the sender and receiver is essentially the same animal, and which is putting clicks out into the sea that need to still propagate through water and then interpret the echoes that come back from prey. So again, thinking about still sound propagation, environmental conditions, and the different characteristics of the sender and receiver. But then another aspect that we need to add to this picture is the prey variables. So different size of prey will be differently detectable. How the prey are distributed, are they in individuals or clusters? And target strength, which is describing how well echoes reflect back from the prey, which is influenced by prey composition. And because air cavities reflect echoes well, fish with swim bladders will have greater target strength than squid, that don't have those twin bladders and maybe more gelatinous in composition. So going to the theoretical study first. So this was published in PROSA and work led by a colleague at DNO, Sander von Bendebecken. And to start building this kind of theoretical model, Sander did an extensive literature search and pulled together all the different parameter values for sperm whale hearing and sound production, including sound directionality, also the ambient noise conditions in different sea states, and characterizing the sonar, received sonar at the whale, which is not just the 1 to 2 kilohertz signal that we put out, but also there's harmonics, especially when the source was at higher level, which then interfere more within the kind of echolocation band of sperm whales. A big data gap in this is the hearing measurements for sperm whales and some other parameters. But for hearing, it really relies on few stranded animals, live stranded animals, that hearing has been tested, and these have been juveniles, so less is known about the hearing and adults. And so Sander was using some parameters from better studied tooth whales, such as dolphins, and then had to extrapolate some of these parameter values. So to incorporate this uncertainty of what the parameters actually should be for sperm whales, he constructed kind of a range of optimistic and pessimistic scenarios for each parameter. And for these ranges, it's also useful to characterize things like the source level of sperm whale clicks does vary. It's not necessarily a constant. So the scenarios that he considered included animals facing towards a masker or away from a masker. So when he says away, that means 90-degree kind of horizontal angle to the source. High versus low click energy source level and prey target strength. And then the different wind noise scenarios. So we use the buffered scale, which is for 1 to 2 is mirror calm to small wavelets. 2 to 3 wavelets to infrequent whitecaps, and then if you go 3.5 to up to 6, is still kind of workable conditions for us. Involves frequent whitecaps to form at the sea surface, and this is something we record as standard in our visual surveys. So it's kind of a data that was easily available to us, but indicates the wind state as we separate that from swell measurements. So here are some of the results. So on the x-axis is the distance to prey, and on the y-axis is the signal noise ratio from the echoes. So as sound travels further in the ocean, and there's two-way travel time, right, from the echolocator to the prey and back, there will be less and less energy coming back to the echolocator, and that's what that decrease over distance is. So on the top panel shows regular clicking, and on the bottom panel is buzz clicking, where the shaded gray area shows the inspection range that is relevant for sperm whales. So for regular clicking, we can infer from the interclick intervals that they search several hundred meters ahead, whereas for buzz clicking, we think it's something more like tens of meters in the maximum. So what you're really looking for in this plot is when does those different scenarios for signal to noise ratio coming back from the prey, when do they fall below the detection threshold, which is in red line. So on regular clicking, some of those scenarios, like the thick gray line, falls below the red detection threshold within the shaded gray area, meaning that there's potential for masking within the relevant inspection range for the sperm whale. So in easier terms, as the whale is trying to listen for echoes further away, it's actually limited to a shorter range echolocation, theoretically, right? Compare this to the buzz clicking on the bottom, and you will see that those lines are further away and don't fall below the red lines within the shaded gray area, indicating there's less masking potential when you consider just the pure are prey detected or not. So this plot shows the outputs for the sonar effects. So we have long range echolocation again on the left, regular clicking, and short range on the right hand side. And now the panels, again, x-axis shows how far animals can detect prey at the 95 probability. So it's the distance again here, and the scenarios are the different rows. And in blue are ambient noise condition, yellow lower sonar levels, and in red is the highest levels. And in the different shading indicates if the sea state is, say, 1, or if it's the sea state, I think, is up to 4 in the densest panels. So again, it shows that the detection range is kind of diminished with increasing sonar level, increasing background noise. And some of those bars are again below the shaded area, which is the relevant inspection range for sperm whales. So one final plot from this theoretical modeling paper I wanted to highlight is this one, where again you have regular clicking and post clicking, and then the different scenarios now in rows. And green indicates where there's lowest potential for masking, so where the detection distance exceeds the largest inspection ranges, whereas red is the greatest potential for masking, so where the detection range was smaller than the minimum inspection range, so kind of limiting again the inspection range of sperm whales. And 2 things I wanted to highlight here. So sonar, when it's received at high levels, has greater masking potential than wind noise up to sea state 4. So in the bottom panel with the high source levels, there's a lot of red boxes compared to the top rows where there's much more green. And similarly here, regular clicking versus bus clicking. So the detection of distant prey by regular clicking is more likely to be affected than the detection of prey via short range bus clicking. So again, this is kind of reiterating the point I made a couple of slides earlier, looking at these detection range plots. So multiple factors affect the potential for masking, both the whale behavior and the source behavior and the ambient noise conditions. And I think this study was really neatly illustrating that. So now to the Marine Mammal Science paper that Carol mentioned earlier. So this is the data-driven study, and here are all the authors and Patrick Miller as the lab head in the last author position. So given all the theoretical work and thinking about this, we set out to formulate some explicit hypotheses before testing them. So this is a table from the paper with a lot of text in it. So I'm not going to talk through all of the text, but I wanted to highlight the 7 key hypotheses, which we categorized as those relating to foraging effort and success, and those that are more specific anti-masking strategies. So from the outset, if animals are influenced by or under auditory masking, we might expect that the foraging gets harder, and maybe so hard that animals will still simply stop foraging. So the first is the reduced foraging effort, and the second is reduced foraging success. And perhaps if the masking influences the kind of foraging efficiency, maybe they need to increase their effort to capture prey. Perhaps the buzzes are longer, for example. And we already know from previous analysis of data that the whales do stop foraging during sonar. But this alone doesn't really give strong evidence that masking is the underlying cause, as whales might simply be startled by the sonar, or they might be afraid of it. So the masking could be just one of the contributing factors that cause animals to stop foraging in the first place. So this is why we wanted to look at these other hypotheses from 4 to 7. So different ways that you could release masking. So the first one I already mentioned is the amplitude masking release. So increasing the signal level. This could be increasing the click level or increasing the echo level. And you could do this by getting closer to the prey field that you're wanting to echolocate at, or perhaps switching prey type to something that has greatest target strength. Then the spectral masking release. So shifting the frequency of the echolocation flex. Now, this is something we decided not to pursue because, as I mentioned, the tag is on the back of the whale. And what we get as a spectral signature with body shielding and everything going on might not be exactly the spectral signature at the source. But we wanted to include it in the table in any way for completeness and for thinking about this issue more broadly. Temporal masking release. So how would you separate the echolocation signals from the sonar signals in time? I'm not exactly sure how sperm might manage to do that, or if certain patterns of sonars, maybe if it's very intermittent, might allow for some temporal masking release. That's a little bit harder question to address. And then the spatial masking release. So this is thinking about the orientation effects. So both the outgoing signal is directional and animal hearing is directional. So something that you hear in front of you is much more easily audible than something that's behind you. So that's something we can measure from the tag because we have the orientation of the animals. The other potential way to release masking spatially is by depth variation. So if the animals, for example, dove deeper, and therefore they're further away from the sonar and potential surface noise. So then we thought about all the different data indicators for each hypothesis, and I have summarized them here in a table of metrics. So we addressed all of these hypotheses except the spectral masking question. So we looked at things like the summarized data for the buzzes. So pause presence following a buzz might indicate prey capture success, buzz duration, buzz activity in terms of acceleration, stroke rate. We looked at first the interclick interval of the regular click train, which is indicative of how far the animals are echolocating at because of the two-way travel time, click rates, facing angle, and depth at the start of the regular click train. And these then entered the statistical analysis as response variables, so the probability of pausing, following a buzz, buzz duration, and so on, with several explanatory variables that were designed to piece apart the kind of orientation effect and potential effect of wind noise. So we had received levels from sonar, orientation relative to sonar, sea state, and orientation relative to sea surface. Again, everything that we get from the movement sensors on the tag. We applied generalized additive mixed models to all of these variables, except for the apparent output level, which, because of clipping in the sound records, we have to use a right-hand censored regression approach. So what did the data look like? Here are the start and end depths of regular click trains and buzz trains in blue, regular clicks are in black, in the 3 different exposures. So no sonar, continuous active sonar, medium level pulse active sonar, and high level pulse active sonar. 40 minutes pre-exposure, 20 minutes ramp up period where the source levels increased both at the source but also at the whale as we are approaching the whale, and then 20 minutes full exposure. And from these, it's not really clear that there are very strong patterns in the data. There's quite a bit of regular clicking and buzzing too going on during the exposures. Oh yes, and here I forgot to mention that the thicker lines indicate the animals facing towards sonar more, whereas the thinner lines are the animal facing away from the source. So it was actually quite tricky for this paper to try to visualize the data because of all the different metrics you need to think about: orientation, the different sea states, the whale foraging is depth dependent, and then the received level, and then the different sonar exposures as well. So I thought I'd walk you through some of the scatter plots that I made to try to tackle this. So here on y-axis is the angle to the sea surface, and on x-axis is the angle to the sonar angle. So the 0 angle means facing towards the surface, 90 means that's horizontal relative to the sea surface, and facing away is 180 surface angle, sorry. And the same for the sonar angle. So facing towards is 0. And this scatter plot shows the data for just the sea states 4 and 5, so when there's frequent wet caps and a lot of foam. And here you can see what you're really looking for is like, are the whales facing away from the sea surface and the sonar when they are loud, essentially. And here you might think, oh, something might be going on because all of the sonar blue and red dots are at the steeper angles. But this could be a small sample size effect, because when you look at all the different sea states, in fact, in the sea state 3 to 4, there's a greater spread, especially during the pulsed-active sonar. So again, maybe you can see some patterns here, but it's a little bit difficult to tell without the statistics. Here's another way of looking at the data. So as a function of depth, I've plotted here the first interclick interval, okay, indicating the two-way travel time for regular clicking. Again, there might be some patterns with depth, not very strong. In any case, here, the red and the blue circles, which are from during the sonar, it seems to be within the baseline range of data, which is shown in gray. And again, with the top panel showing the mirror count to small wavelets to then increasing sea states and greater wind noise on the bottom. Here's the same plot for click rates. So unlike the buzz clicking rates, the regular clicking rates actually increase as a function of depth. And you might think, oh, maybe at the higher sea states, there is, a greater increase as a function of depth. But again, it could be a small sample size issue. And also, when we were further offshore, you really get the roughest conditions and biggest sea states. But that's also where the foraging habitat is deeper. So these guys do forage at the bottom in these areas. And again, what I wanted to highlight here was that the red pass and blue cast exposures seem to be quite well within that baseline behavior range. So then doing the statistics, the most supportive effects were these depth-dependent effects rather than the sonar effects. So here I plotted the model predictions as a function of depth for probability of pause following a buzz, the buzz duration, buzz odd as a function of depth. So the buzzes were followed by a pause more frequently at the deeper depths, and buzzes were longer and they were more active in the shallower depths. So again, kind of confirming what we've already found in the 2018 paper for this kind of depth-dependent foraging. There seemed to be some support for effect of sea state on kind of reduced buzzing probability at the shallower depths. But again, it's quite within the range of baseline effects if you look at the probability of buzzing as a function of depth. There's interclick interval and click rates as well were depth dependent, but those had little effect of sea state. So yeah, this is the point I already made. So buzz occurrence reduced at high sea states, especially at shallow surface angles and in depths of less than 500 meters. So do whales click louder when it's noisy? So is there a Lombard effect? As I mentioned, there is the issue of loud clicks being clipped in the TAC record. So even when we looked at just the lower gain, so there's two channels in the hydrophone, and the one has its gain lowered down specifically for this. But we still had 20% of the data that were clipped. And so that means we know that the clicks are loud, but we don't know how much more than we can actually record. So for this, we analyze this data as kind of a right-censored variable where we know the minimum value, but we don't know the exact value of those loud clicks. Again, I looked into several different ways of visualizing and trying to see if there were any patterns in the data. There weren't any super clear patterns that I could see, but fitting the Bayesian models and looking at null models as well, there seemed to be support for a small increase in the click levels, in the apparent click levels, again measured on the back of the whale. So on the top is the visible change in the 0 to peak level of the clicks as a function of depth. And here are the predictions for different sea states, so 2, 3, 4, and 5. And you can see that the expected increase in the click level decreases as a function of depth, and more so less so when the whale is horizontal to the sea surface rather than facing to the sea surface. And on the bottom, again, similar prediction plot from the model. So the change in click level on y-axis with different sea states, but now as a function of the vertical angle, so facing towards sea surface versus facing away. And that's a few dB change there. And the model did support some small effects of sonar as well when it was at higher levels. So here, perhaps you can't see it, but there's a label for 170. So there was one of the highest received levels at the whales. And in those instances, the model estimated that at the 0 to peak level of clicks increased by about 4 dB. But again, this was limited to when the whales were facing the source. And the model prediction here are given for sea state 1, so it's showing just the effect of sonar rather than the sea state. So what did we learn from all this? I'd like to circle back to the kind of masking potential factors for echolocation. So there's many factors to consider, and a lot of these factors are not under our control on the field. But we still feel optimistic that you can tackle this with certain key measurements and perhaps with a different species. So one key measurement for future studies is the received level and spectra of the anthropogenic noise itself. So, and I think we did pretty well with this using the DTACs and the hydrophones. I think that's a very good approach to measure the dose of sonar. Ambient noise levels. This was more difficult for us because as the whale is moving through the water, it's generating flow noise and self noise, which masks the ambient noise. And so we did attempt to make some ambient noise level measurements, but it was masked for too often that we couldn't use it as a covariate, and that's how we ended up using the sea state and orientation towards sea surface as the kind of proxy for what the ambient noise conditions might be. Animal source characteristics. So you can get some measurements with the animal attached tag approach, but another way to approach this would be to use some sort of towed array or some other passive acoustic monitoring system to get at the levels that the whales are actually clicking at in their beam rather than open axis. Animal behavior, and this is where I think the animal attached tags are really powerful in kind of characterizing of how animals might be compensating for masking behaviorally. And finally, again, talking about the sufficient sample size, because there are so many different factors, you need to really have a large number of measurements to fill in all of the combinations of the different masking conditions and sonar conditions or other masker conditions. So my take homes would be that auditory masking is influenced by many factors, including animal behavior, which is why it is so difficult to detect, but it's still important to detect. And so these are challenging to design as we need to estimate both signal and masker levels. And for the results, so we found preliminary support for the effect of sea state and probability buzzing and apparent source levels when the whales were facing the surface at shallower depths. So in this data set, with the sonar exposures being quite brief and low level, and something we already expected based on the theoretical modeling study, the reduction in foraging effort to success may be driven by other factors than auditory masking. And I think that's me. And I just wanted to give heads up to and kudos to all the co-authors and field workers and data analysts and funders and the many collaborators that have made this work possible. Thank you.
Thank you for that presentation. I think we are getting close to 1 o'clock here, so I think I do see there are a couple of questions. So I'm going to turn it over to Eric or Aisha. Are you taking care of questioning?
Yeah, I'll take care of the questions.
Okay, great.
First of all, thank you, Saana, for a really interesting presentation. I'll just start with the first question. It was by Patrick Lynn. What were the frequencies used by HPAS and MPAS and CAS? Were these all the same?
Yeah, so they were all 1 to 2 kilohertz hyperbolic upsweeps. But like I mentioned, they are harmonics at the source. So especially at the higher source level, there's kind of harmonic interference at the higher frequencies, which is likely to affect their masking potential.
All right, the next question is by Elizabeth Yang. Are these papers available by open source? I guess she means the papers that you mentioned during your talk.
I don't remember, but both Sandra and I are in ResearchGate, and we are always very pleased if anybody messages us and forward the paper. So please email me or send me a message on ResearchGate or on Twitter as well. I'd be very pleased to share.
Okay, next question is by Thomas Zoutis. Are there differences in sound capability volume levels between larger and smaller sperm whales? If so, are certain demographics, specifically smaller whales, at a high risk to underwater noise generated by humans?
That's a really interesting question. I often wonder about juvenile whales having more limited behavioral options. I guess I haven't thought about so much about how they might be limited in terms of the acoustic generation. And it's not something that we have data on. So I don't think I can give you a very informed answer to that, I'm afraid.
Okay, one more question by Claire De Vendel. How was it possible to obtain audiograms for sperm whales?
Yes, another great question. I think I would have to refer back to Sander's paper, but I think you can make some assumptions of where the sensitive hearing frequencies are based on the sound production, so you can measure the actual kind of spectral signature of their produced clicks, which are very broadband. For hearing, again, I think the only hearing measurements are direct for sperm whales are those stranded juveniles, so they might not be totally representative. So that's definitely an area that would need further work on if we can get over some of those logistical challenges.
All right, another question. Annabelle Westel is asking, is the figure with 4 plots of type profiles recorded during different exposure levels included in the published paper?
So that is, yes, so that particular figure does pull the different receive levels. So, but I did look at, I did try to visualize some of those plots with bigger symbols indicating greater received level. But you're right that that plot did pull the different exposures. And so the first 20 minutes would be the ramp up period when the received levels are slowly escalating, and that the full exposure period is when you can expect the highest levels. Of course, sometimes depending on the whale behavior and how the logistics go on the field, we don't achieve very high levels in each experiment. And anyway, they are fairly low levels, across the board. But yeah, there will be some experiment variation.
Okay, and I think this is the last question. It's by Gisela Giardino. She's asking if the click rate is calculated as number of clicks per second. She missed that part.
Yeah, yes. So it's clicks per second, and I used the total clicks in the click train. No, actually, I correct myself. I used the median interclick interval and took the inverse of that, because sometimes we did have some false positive detections, which would generate unrealistically high click rates. And so that was actually another challenging part of the acoustic analysis, was trying to make sure that the acoustic measurements were not themselves masked or having false detections.
Okay, I think these are all the questions from the audience. Daryl, on to you.
Okay, well, we're just short of 2 o'clock, not 1 o'clock, I think I said earlier. So we're coming to an end. So if we have no further questions, maybe I'm going to ask you one question to finish off the question session. So would you expect ship noise to have a greater potential to mask sperm whale echolocation, given it's a continuous chronic noise, than pulse Navy sonar?
Yeah, I think this is a really important and interesting question, and we should for sure be studying that. So yeah, we need to keep in mind that there's many chronic noise sources, and that have increased over the past decades, that would have greater temporal overlap and that have more chronic over time, because of, especially in busy areas of, say, Europe or the east coast of United States. And of course, then in many types of vessels as well. So perhaps some of them will be that low frequency that they wouldn't affect perhaps sperm whales as much, but they might affect baleen whale communication more. Yeah, I think definitely that is something that we should keep considering, and keep considering that here for this particular paper, though we didn't find strong impacts of Navy sonar in terms of masking. Perhaps it's not surprising, because it's quite a defined tonal signal compared to some more broadband masking might have greater masking potential.
Okay, great. Thank you for that. Well, thank you very much for an excellent presentation. We had a really good size audience. I saw it was up over 120. So obviously a lot of interest in the topic, a lot of interest in your work. Thank you very much. We appreciate it, and good luck on future research.
Thank you so much, and thank you for having me. Appreciate
You're
it.
welcome. All right, I guess with that, we'll end today's seminar, and look forward to a presentation next month as well. Pay attention to the Marine Society for Marine Mammalogy website for announcement of the time and topic of the next seminar. Thanks much. Bye-bye.